Welcome, everyone, to another deep dive. We're diving into quantum mechanics today.
Oh, yeah. Always a fun one.
It really is. And to help us navigate this fascinating but tricky subject, we've got Richard Feynman's Feynman Lectures on Physics.
A classic.
Yeah, and we're focusing on chapter 38, where Feynman tackles the relationship between waves and particles.
Yeah, he was amazing at taking something really complex and making it understandable.
Exactly. So if you've ever wondered how something can be a wave and be a particle, this one's for you.
That's the heart of it, isn't it? It really forces us to rethink how we normally see the world.
Yeah, in our everyday world, it's like, okay, is this thing a wave like sound, or is it a particle like a grain of sand?
Right, but quantum mechanics says, nope, not that simple.
Exactly. It's like trying to explain what color is to someone who can only see black and white.
Love that analogy. Quantum mechanics says that at the subatomic level, those old categories just don't work anymore. We need new tools like this idea of amplitude.
Amplitude. Okay, so it's not just about saying the particle IS here, right?
Right? Instead of a definite location, amplitude gives us the probability of finding the particle at a certain place in time.
So it's more like a map of maybes than a pin on a map?
Exactly. It's inherently uncertain where that particle is until we actually try to measure it.
And that's where my brain starts to hurt. It's not that our measurements are just a little fuzzy. The uncertainty is built in, right?
It's built right in. And Feynman had this great example, a single slit experiment.
Well,
Imagine you shine a beam of light through a tiny slit. Now think of that light as a stream of particles, photons. What should we see on the screen behind the slit?
okay, if I'm picturing this, I'd expect a bright spot right behind the slit where all the photons hit.
Right. That's our everyday intuition. But that's not what happens. Instead, we get this pattern of bright and dark bands spread out on the screen.
Right, that sounds
Like waves, called a diffraction pattern, and it's what we usually associate with waves.
so we're shooting individual particles, but they're acting like waves.
Exactly. They interfere with themselves like ripples on a pond.
Okay, that's seriously weird. But what if we try to cheat and see which path each photon takes through the slit?
Now you're asking the really good questions. If we try to be clever and measure precisely which slit each photon goes through,
Does the pattern disappear?
it does. It's like the photons knew we were watching and decided to act like good little particles again.
So it's all about the act of observing. This is blowing my mind.
That's the essence of the Heisenberg uncertainty principle.
So we've got these particles acting like waves, all this uncertainty. It makes you wonder how anything in the subatomic world behaves predictably at all.
It's a question that puzzled the pioneers of quantum mechanics.
Mm.
For example, if electrons are like waves, why don't they just spiral into the nucleus of an atom?
Yeah, that's what classical physics would say, right? A negatively charged electron should be attracted to the positively charged nucleus.
Exactly. But atoms are stable. They don't just collapse. And that's where quantum mechanics revolutionized our understanding of how atoms are structured.
Okay, hit me with it.
Well, quantum mechanics says that electrons in an atom can only exist at specific energy levels. It's like a staircase. An electron can be on this step or that step, but not in between.
So instead of smoothly moving to a lower energy, the electron has to make a quantum leap.
Exactly. It's like there are these invisible energy tracks the electron has to follow. This is where the Bohr model of the atom comes in. It's a simplified model, but it helps us visualize these quantized energy levels.
So we're picturing the nucleus at the center, and the electrons are zipping around in these specific orbits.
Exactly. Each orbit represents a distinct energy level. And you might be wondering why these particular orbits are special.
Yeah, what's stopping the electron from hanging out somewhere between these levels?
The Heisenberg uncertainty principle. If an electron got too close to the nucleus, we'd know its position very precisely.
But then we'd know less about its momentum and its energy.
Exactly. The electron's energy would go through the roof if it were squeezed into such a tiny space. It'd be like trying to stuff jumbo marshmallow into a tiny piggy bank just too much.
So the electron wants to get near the nucleus, but the uncertainty principle says, nope, gotta keep your distance.
Right. The ground state of an atom, its lowest energy level, is that perfect balance between these forces.
Wow. So quantum mechanics explains not only why electrons don't crash into the nucleus, but also why atoms have a size and shape at all.
It does. And it goes even further. These quantized energy levels also explain why we see those specific spectral lines when we look at light from different elements. Each element has its own unique set of colors.
Right, like those emission spectra we see in chemistry.
Exactly. When an electron in an atom jumps from a higher energy level to a lower one, it emits a photon. a particle of light.
Like jumping down a step on that energy staircase we talked
You
about?
got it. And the energy of that photon corresponds to the energy difference between those two levels.
So a bigger jump means a higher energy photon.
And since the energy of a photon determines its color, those specific energy jumps create those unique spectral lines we observe.
It's like each atom has its own song, and those spectral lines are the notes.
I love that. And it's the fact that these energy levels are quantized that we get these clear, distinct notes instead of a jumbled mess.
We've been talking about how quantum mechanics shapes the world of atoms and particles, but it makes you think about the bigger picture, doesn't it?
You mean the philosophical side of it all?
Yeah. If we can't even know both the exact position and momentum of an electron, does that mean the universe is fundamentally unpredictable?
It's a huge question, and it's one that's been debated for decades. It really challenges that old view of the universe as a perfectly predictable clockwork mechanism.
It does. But even before quantum mechanics, there was chaos theory, right? That butterfly effect idea. Didn't that already mess with the idea of perfect predictability?
Absolutely.
Yeah.
Even in classical physics, true determinism is more of an ideal than a reality. Think about a simple coin toss.
We usually say it's a 50-50 chance.
Right. But imagine we knew every single factor, the force of the flip, the angle, the air resistance, even tiny imperfections on the coin.
Hmm.
Theoretically, we could predict the outcome perfectly.
Okay, in a perfect theoretical world, maybe. But isn't that impossible in reality?
Exactly. In the real world, there's always some tiny error in our measurements. And those tiny errors can compound over time.
Yeah.
That's chaos theory in a nutshell.
So even without quantum mechanics, those tiny uncertainties would eventually throw off our predictions.
Precisely. It's a matter of scale and time. Even with super precise measurements, eventually our predictions will diverge from reality.
It's kind of humbling to think about. Whether it's classical physics or the quantum world, there are limits to what we can know for sure.
It is humbling. But here's the exciting part. That doesn't mean we stop exploring and asking questions.
Yeah.
We keep pushing the boundaries of what we know.
Exactly. So as we wrap up our deep dive into quantum mechanics, what's the one big takeaway you want listeners to leave with?
Embrace the mystery. The universe is full of surprises, and our understanding of it will always be growing. What seems weird and counterintuitive today could be tomorrow's breakthrough discovery.
I love that. And it reminds me of something Feynman himself said. I think I can safely say that nobody understands quantum mechanics, but that doesn't mean we can't be amazed by it and keep exploring its mysteries. So keep asking those big questions, keep exploring, and never be afraid to dive into the unknown. Thanks for joining us for another deep dive.